Hello, and thank you for joining us for the second course in our Introduction to CONVERGE 3.0 webinar series. Throughout this series, we will not have time to answer questions, but we do encourage you to contact us directly with any inquiries that you may have, and that contact information will be provided on a slide at the conclusion of the course. Um, Today's course is focused on inlaid mesh enhancements, and if you're interested in attending any other webinars, they are available on our events page of our website. And today's inlaid mesh enhancements presentation is going to be given by Karthik Reddy. He's Principal Research Engineer in Development here at Convergent Science. Again, thank you for your time today, and I will leave you in the hands of Karthik.
Thanks, Tiffany. So let me get started on my presentation here. So I'll be talking about what an inlaid mesh is and why we would want to use one. Then I'll be talking about how to create an inlaid mesh using CONVERGE Studio, and I'll demonstrate that using a couple of example cases. Finally, I'll be talking about a few things to keep in mind in order to get a good quality mesh when you're generating the inlaid mesh in Studio. So what is an inlaid mesh? It is a separate grid type in CONVERGE, which is not part of the Cartesian cut cell mesh that CONVERGE normally uses. So the inlaid mesh can be made of any number of cells, and they can be of any shape, size, and orientation. And they can be used to cover a certain portion, any portion of the domain, or if you choose, you could cover the entire domain with an inlaid mesh. Typically, you would generate the inlaid mesh in CONVERGE Studio, and like other boundaries in CONVERGE Studio, these inlaid meshes would be defined by surface triangles, which will be defined as flow-through boundaries. So I want to mention that inlaid meshes are completely optional in CONVERGE. So say you had a case that you've been running in CONVERGE with older versions like 2.4. Those cases will run perfectly fine with 3.0. However, with 3.0, the user now has the option to specify a grid of their choice to cover a certain portion of the domain. So you can use the inlaid mesh to take advantage of a priori knowledge of the flow. So for example, if you have a spray in your domain, you could create a mesh that's oriented along the direction of the spray. Or let's say if you have a boundary layer in your mesh that you would like to resolve, say around an airfoil, for example. Then you could cluster the cells near the airfoil by creating an inlaid mesh as such. In general, it is possible to get more accurate results using an inlaid mesh with fewer cells compared to achieving the same results using an equivalent Cartesian mesh. So inlaid meshes are typically created in CONVERGE Studio, and I'll be demonstrating a couple of cases for creating the inlaid mesh. So broadly speaking, there's two types of methods for creating the inlaid mesh. So one is creating a shaped mesh that's not attached to any other boundaries. So for example, if you have a spray, you'd like to create an inlaid mesh which is conical and which surrounds the spray. And that inlaid mesh wouldn't be touching any other surface. Alternatively, you could also extrude an inlaid mesh from a triangulated surface. So if you have a wall boundary, you could extrude that wall to create an inlaid mesh near the wall so that you can capture a boundary layer there. Studio also offers the option to import a plot3D file. So once you do that, Studio will create the appropriate surface triangles using the grid points specified in the plot3D file. So at this point, I would like to switch to Studio. So here we have a very simple case. It's just a cylinder, and we have an injector inside this cylinder. So let me hide these boundaries. So as you can see, we have one injector which has 8 nozzles in it, and our goal is to create an inlaid mesh for each of these nozzles that is oriented along the spray direction. So to do this, I'm going to go into spray modeling, click on injectors, and then click on edit. And here, click on nozzles. So I'm bringing this up just so that I can get the location of the injector. So that's provided over here. Now, since we want to create an inlaid mesh for these nozzles, first you can see the inlaid mesh tab here. Click on that. And here you have a shaped mesh. And under shaped mesh, you click on cylindrical. So our goal here is to create a conical inlaid mesh around these nozzles. And if you think about it, a cone is nothing but a cylinder with 2 different values for the radius on either side or on either ends. So we would like to create a cylindrical mesh that begins at the location of the injector, which I copied before. And for this radius, you can say 0, which is fine. For center 2, this would be the other end of the cone, and this would determine how long your cone is. So in my case, I'm going to say a little over 2 centimeters. And now we want to specify the radius at the end of the cone. So this would depend on what the cone length is and what my spray angle is. So for my particular setup, this is an appropriate value. And next we have DR and DH. So these define the size of the inlaid cells that we'll be creating. So DH refers to the cell dimension along the length of the cone. DR is the dimension both along the radial direction and the angular direction. So for my case, I'm choosing something that's appropriate. And now I just click apply. Okay. So here you can see that Studio has created an inlaid mesh that starts at the injector location. So now our next step is to actually orient this inlaid mesh along one of these nozzles. So to do that, I'm going into here. We'll click on the Transform tab, and then we click on Rotate, and then we click on Selected Boundary. So before I go further, I just want to mention something very quickly. When we created the inlaid mesh, Studio creates 2 additional boundaries known as inlaid interior and inlaid exterior. So the inlaid exterior refers to the outermost layer of triangles for the inlaid mesh. So if I hide that, it reveals the inlaid interior boundary, which makes up all of the interior triangles for the inlaid mesh. So the inlaid mesh is always made of at least 2 boundaries, one which defines all the interior triangles and the other which would define just the outermost layer of triangles. Okay, so coming back to what we wanted to do. So we wanted to translate and rotate the inlaid mesh that we generated so that it is aligned with one of the nozzles. So I will rotate this first, and here I click Selected Boundary, and these are the 2 boundaries which make up the inlaid mesh, which I want to rotate. So let's say I wanted to rotate it about the y-axis, I want to rotate about the injector location. And for my case, the spray angle is 60 degrees. So I'll specify that. And then I click apply. So now it's been rotated. Now I need to translate it so that it lines up with the nozzle. To get the location of the nozzle, so previously we opened up this injector tab to get the coordinate for the injector. So in the same tab, you have the nozzle properties as well. So you can click on edit. In this window that pops up, you have location and orientation. So if you click on that, you have the nozzle radial position. So this refers to the offset of the nozzle from the injector location. So that's the amount by which you would want to translate the inlaid mesh. So here, I'm going to click on translate, selected boundary, and then I'm going to choose the two inlaid boundaries. And let's say I want to translate along the x-axis. The translation amount is the offset for the nozzle radial position. And click apply. Okay, so now we can see that the inlaid mesh has been translated and rotated so that it is oriented along the one of the nozzles here. So the next step is to create an inlaid mesh for all of the other nozzles. So an easy way to do this would be to just make rotational copies of this inlaid mesh for all of the other nozzles. So you can do this by going into transform, rotate, selected boundary, and select the inlaid boundaries again. And this time, so the injector nozzles are rotated about the z-axis. So I would like to do the rotation about the z-axis as well. And the rotation origin is again the injector location. And here I have 8 nozzles, so that's 45 degrees. And now this time I would like to make copies as I rotate. So I would like to make 7 copies, plus the original I have should cover all 8 nozzles. And click on apply. So at this point, as it copies the inlaid mesh, Studio is also able to figure out that these are all inlaid meshes that it is creating. So when it creates all these new triangles, it keeps them in the right boundaries. So for example, inlaid exterior would now refer to all of the outer triangles for all of these inlaid meshes. And inlaid interior, so if I hide this, inlaid interior would refer to all of the triangles that make up the actual inlaid mesh. So now you can see that we have 8 inlaid meshes that are oriented along each of the nozzles. And we're done creating the inlaid mesh for this case. So now you could actually go ahead and export this case, and you can run it with CONVERGE 3.0. So going back to my presentation, so here's a image showing what the inlaid mesh looks like in TechPlot. So we have the inlaid cells that are oriented along the spray direction, and they are surrounded by Cartesian cells. So for this case, we used additional layers of embedding on the outermost boundary of the inlaid mesh. So that's why you can see that there is some embedding around it. So the reason for this embedding is going from an inlaid cell to a Cartesian cell, you'd like the cell sizes to be about the same size. This helps with stability. So that's why we have these additional layers of embedding over here. And in here, we can see the spray penetration for the case that I just showed. So the dotted red lines can be seen on these two movies corresponds to equal radial positions as the spray penetrates. So as you can see, as the simulation progresses, the sprays from all of these nozzles penetrates an equal distance as it goes through the inlaid mesh. If we use just a Cartesian mesh for sprays, it is possible that the nozzles that are oriented along the principal axis, along X, Y, and Z, may have slightly different penetration compared to what you might see for the nozzles not oriented along the principal axis. So this difference can be small, depending on the case. But if you want to get rid of that difference altogether or try to reduce it as much as possible, then using an inlaid mesh would be a good idea. So here for this particular case, we did notice that using the Cartesian grid, there is a small difference in the spray penetration between the nozzles oriented along the principal axis versus the nozzles not oriented along the principal axis. So for this particular case, if we used an inlaid mesh as shown on the left, we were able to reduce that difference to a very small amount. Whereas trying to achieve the same difference with a Cartesian mesh, we would have to use more number of cells as shown on the right-hand side. So this goes to the point that you could use an inlaid mesh to get more accurate results by using a fewer cell counts compared to an equivalent Cartesian grid. So I mentioned that there's a couple of ways to generate the inlaid mesh. So we just looked at one of those ways, which was creating an inlaid mesh that's separate from any existing boundaries. The next example I would like to talk about is creating an inlaid mesh by extruding a surface. So let me go back to Studio again. So to demonstrate this, we can look at a flow bench case here. So for those of you who aren't familiar with flow benches, it's a device that you use to test the internal aerodynamic qualities of your engine components, say, for example, your intake and exhaust ports. Typically, for a flow bench case, you would fix the valves at a certain position, and then you'd prescribe either a total pressure boundary condition or a mass flow rate, and then take a look at what the flow looks like. So for these kinds of cases, the results you get can be sensitive to the amount of resolution that you use. So it makes sense to use an inlaid mesh so that you can better capture the boundary layer around the valves or along the intake and exhaust ports for this case. So this particular case is an exhaust flow bench that we're looking at. And let's say we wanted to create an inlaid mesh for this case. So let me hide these boundaries. So say we wanted to create an inlaid mesh around these valves. So what we could do is we can go into inlaid mesh, and under inlaid mesh, this time we want to extrude existing triangles. So we click on extrusion, and in here we want to select which triangles we want to extrude. So I can go in and select all of the triangles that make up the valve. And in the extrusion layer settings, we have to specify what's my initial distance going to be. So this tells me what the first wall normal cell spacing will be for my inlaid mesh. So let's say 0.1 millimeter. And then you'd have to specify 2 additional parameters. So let's say I would like to specify how many layers I want. So let's say 5 layers. And let's say I would like to specify an expansion ratio of 1.1. So an expansion ratio tells you how the wall normal spacing should change as we go from one layer to the next. So what this means is the first layer will have wall normal spacing specified in this initial spacing. The second layer will have a wall normal spacing which is 10% higher than the first cell. And the third cell will have a spacing that's 10% higher than the second cell, and so on. So that's what this expansion ratio means. So once we have specified this, we have selected the triangles that we want to extrude. And now I just click apply. And just like I mentioned, or just like we saw with the previous example case, CONVERGE realizes, the studio realizes that the triangles that it's creating are part of the inlaid mesh. So it puts them into separate boundaries called inlaid interior and inlaid exterior as shown. And like before, inlaid exterior refers to the outermost surface, and inlaid interior corresponds to all of the surface triangles that make up the inlaid mesh. So for both of the example cases I showed, as soon as you create the inlaid mesh, if you look under grid control, you'll notice that we have an inlaid mesh checkbox and it has already been checked. So Studio can figure out that as soon as you use the inlaid mesh to create a mesh, it knows to turn this flag on. And if you click on inlaid mesh here, it has also already selected the interior triangles, which is what you want to select. So you do not want to select the outermost layer of triangles here. This has to do with how CONVERGE generates the inlaid mesh. So once you create all these triangles, Studio automatically selects the right boundary that needs to be exported. And that's it. So the inlaid mesh has been extruded around the valves, and you could just export this case and run it with CONVERGE 3.0. So going back to my presentation here. So here's a look at the inlaid mesh in TechPlot. So in addition to the inlaid mesh around the valves, we did extrude the surrounding triangles, some of the triangles in the port, as you can see here. So on the left-hand side, you have an overview of what the mesh looks like, and on the right-hand side, you have a closer look at the inlaid cells and the Cartesian cells that surround it. And here's a look at the velocity contours for this particular flow bench case. Here's another case for which it might be useful to use the extrusion feature. So we're looking at a turbine blade here. And what we have done here is we've created an inlaid mesh around the turbine blade, as you can see here. And on the right-hand side, we're looking at a certain small section of the turbine blade. So this mesh over here is the inlaid mesh. It is being surrounded by the Cartesian mesh, and this is part of the fluid domain. So the turbine blade starts where we have this red mesh starting. The red color mesh corresponds to the mesh on the solid side, so that's inside the turbine blade. And as you can see, even inside the solid domain, we have three layers of inlaid cells on the solid side, and then we start off with the Cartesian mesh again. We also have some cooling holes inside the turbine blade, as can be seen here, as well as on the images on the left. And inside the cooling holes, which will be the fluid domain again, we're having another inlaid mesh inside, and then we have the Cartesian mesh in here again. So you could choose to create the inlaid mesh for any boundary you like, and it can be any number of layers as shown with this example. And then here's a very simple example of another case where you might want to extrude to create the inlaid mesh. So this is just a flow over a cylinder, and on the left we have the cylinder and the extruded inlaid mesh around it. And then we have the Cartesian mesh that surrounds the inlaid mesh. And on the right is a movie of vortex shedding that we got using this particular mesh. So now that we've seen how to create the inlaid mesh in Studio, there are a few things that we would have to keep in mind when we're generating the inlaid mesh. And that's with regards to mesh quality. So typically, when you're just using Converge's cut cell approach, Converge takes care of the mesh quality automatically. But when you're generating the inlaid mesh, you need to be careful when you're creating it so that you end up with a good quality mesh. Towards this, we have added a new variable that you can specify in post.in called mesh quality. And this will output several mesh quality metrics that can help you determine if there are any problem areas in your mesh. So I'll talk about this a little bit later on. So with regards to mesh quality, there are a few things we would like to keep in mind. So the first thing that we need to think about is surface triangulation. So here we have two images showing two different types of triangulation for the same surface. So the image on the left has a lot of uneven triangulation here. Now, if this was a regular Converge case, then the triangulation on the left is perfectly fine. You can use it to run Converge, and it should be able to handle this triangulation without any issues. However, if you wanted to extrude this surface to create an inlaid mesh, then you can have problems. So the uneven triangulation here will result in inlaid cells that vary a lot in terms of size. So you could have small inlaid cells right next to very large inlaid cells, or you could have long, thin cells, which you might end up with if you extruded this surface. So these kinds of cells can lead to problems in terms of stability and accuracy. So if you wanted to extrude this surface to get an inlaid mesh, then you would have to retriangulate it to look like something as shown on the right-hand side. So another aspect that is tied to the surface triangulation is the shape of the inlaid cells you can get. So in the image that's shown here, we have an inlaid mesh that was extruded from a wall boundary. And as you can see, there was a sharp corner at the wall, which, and we just have two triangles going over the corner. So what happens is when we extruded this particular wall, we ended up with inlaid cells that look like these. So we have inlaid cells over here, and their neighbors are oriented about 70 degrees or so with respect to them. So this kind of highly non-orthogonal or skewed inlaid cells can result in numerical instabilities. So for this particular case, what we noticed was these problem cells were causing a lot of recoveries in the solution. So a way to fix this would be to either add more surface triangulation here so that you have more inlaid cells resolving this corner, and that helps in improving the stability and accuracy of the simulation. Another thing to keep in mind in terms of mesh quality is what the Cartesian inlaid interface looks like. So we have two images over here. The image on the top, we can see that for one Cartesian cell has a lot of inlaid neighbors. So if we're looking at the Cartesian cell at the top left corner. So that would be this Cartesian cell. He has a lot of inlaid neighbors. And one cell having too many neighbors across the Cartesian inlaid interface can lead to stability and accuracy issues again. So to avoid this, it might be useful to have some kind of embedding around the inlaid mesh so that going from the inlaid to the Cartesian cells, the cell sizes are about the same size. This can be achieved either by using some kind of shape or boundary embedding, or you could use a new AMR criterion in 3.0 called AMR inlaid neighbors. So what this does is this looks at the Cartesian cell and checks to see how many neighbors it has across the Cartesian inlaid interface. So if a given Cartesian cell has too many neighbors, too many inlaid neighbors, then it will try to embed that cell. On the other hand, if the Cartesian cell is much smaller than the inlaid cell, so we have the situation that's the opposite of this image shown here. You have one large inlaid cell that's interfacing with lots of Cartesian cells. So in that case, this particular AMR would try to release the embedding on the Cartesian side. So I mentioned briefly that we have a new variable called mesh quality that we can specify in post.in. So if you specify that, Converge will write out several mesh quality metrics to the post file, such as aspect ratio, non-orthogonality, skewness, number of inlaid neighbors, number of Cartesian neighbors, and phase warpage. So all of these can help you determine what are the potential problem areas in your mesh, and you could make changes accordingly, such as adding or removing embedding or changing the inlaid mesh. So there are some restrictions for the inlaid mesh in Converge 3.0. Currently, you cannot create an inlaid mesh that's attached to a moving boundary, and you cannot define the inlaid mesh itself to be moving either. You also cannot have the moving boundaries and the inlaid cells intersect. Currently, we also do not allow for any embedding or AMR for the inlaid cells themselves. But you are free to use any kind of embedding or AMR for the surrounding Cartesian cells. So if you'd like more information about the inlaid mesh feature, I would encourage you to look up section 6.6 in the Converge manual. And if you'd like more details about creating the inlaid mesh in Converge Studio, please look up section 2.3.8 in the Converge Studio manual. We are also planning to offer inlaid mesh training in the near future. So keep your eyes open for that. So I'd like to thank you all for attending this webinar. And I'd just like to mention again that we are offering other webinars as shown here. And you're always welcome to send in your questions to any of our sales or support engineers to the email addresses listed here. And if you'd like to stay up to date with any inlaid mesh training or any other kinds of training, I would encourage you to sign up for our mailing list if you haven't already. So you can go to convergecft.com and sign up, and you'll be notified if there's any new training coming up. So once again, thank you all for attending this webinar.